Hello, everyone. Thanks for having me here. Um, so, yeah, just to reiterate, Fiona Luhrmann, Oregon State University, PhD candidate. And I'm going to be going over some of my recent research work, which is currently in review um, for publication. And yeah, the title of this talk, Ionospheric Anomaly Detection and Source Geolocation over Open Ocean with GNSS Remote Sensing. All right, let's get started. So to get into this topic, it's important to have a little bit of background about what we'll be discussing, specifically the ionosphere. We'll get into that GNSS and coseismic disturbances detectable in the ionosphere with GNSS. So first off, right, what is the ionosphere? It's the Earth's outermost atmosphere layer. We can see a representation here. I would say actually a photograph of when you can see the ionosphere, right? This is an aurora taken from the ISS. And so it's a great representation of kind of what we're talking about when we talk about the ionosphere. Um, Right, it's composed of ions, electrons. It behaves physically as a plasma. Um, and it has a lot of dynamic qualities to it. Um, and I think two of the kind of important ones that we touch on here are night and day behavior. So you can see in the illustration from Pool, during the day we have these four kind of distinct layers of different densities and chemical components, D, E, F1, F2. And then at night, we see that D and E disappear, kind of go back into neutral atmosphere, and F1 and F2 combine to F. So there's a daily cycle that we see in ionospheric behavior. And the other with the Anderson, let me just say the Anderson image here, we see the ionosphere understood in altitude. And so what we're looking at is 90 kilometers to 1,000 kilometers altitude above sea level. And we can see here the D region, E region, F region, and topside, all having different characteristics. But you notice here is that the highest density layers and actually the largest slice of the pie or slice of the sandwich is this F1, F2, or just generally F region layer. And what's uh, important about my research and kind of how we're able to detect things, right, is the ionosphere is heavily impacted by events from above it, right? So that would be space-based events, space weather, such as coronal mass ejections, but also events from below. And what we'll get into is specifically earthquake events there. Now, moving into GNSS, kind of just a basic understanding of what signals are being transmitted from satellites down to ground-based receivers. Which one we care about is the carrier phase measurement. So this is it's essentially a radio wave that we're using to do position navigation, right? The purpose of GNSS. Um, and we can see that there are many different frequencies that these are broadcast from the satellites at. And what I'll say here is the ionosphere is often measured with radio wave sensors, one being like incoherent scatter radar. And the GNSS, uh, for GNSS, the same idea applies, right? This is a radio wave. Only with GNSS, this radio wave is actually passing straight through the ionosphere. It's not getting reflected and refracted uh, and lost because of those impacts. So it's actually at a much high frequency. It can pass straight through the ionosphere, but it passes through with some issues. And so these issues are kind of illustrated here. We do see refraction uh, as it passes through the ionosphere. It's not completely lost. We still have that ground receiver retain the signal. But what's interesting and something we can take advantage of is those different frequencies that the carrier phase measurement is being broadcast at respond differently as they pass through different densities in the ionosphere. So just to say that again, different frequencies are going to be affected differently as they pass through the ionosphere. Because we have 2 up to 3 frequencies that the satellites broadcast at, we can actually look at the differences between these frequencies and measure ionospheric densities. So this is the fundamental system that is GNSS remote sensing of the ionosphere. And here we see the mass, I guess, behind how this works, right? So the difference between 2 different frequency signals are directly proportional to what we call slant total electron content along the receiver transmitter line of sight, right? So satellite, ground receiver, this is the line of sight. And what we're doing is measuring ionospheric electron density here. And just to be clear, this is an integrated measurement. So other radar measurements can measure at different altitudes, the density at this altitude versus this altitude. This system does not. So this is a single value for the entire line of sight that you're seeing here. Also something just to have in mind as we talk about uh, GNSS, line of sight. And so how this then translates over to earthquake detection. Um, so earthquakes generate an acoustic pressure wave. And we can see kind of this illustration trying to allude to this extremely complex dynamic system. We have a source location here. We have a wave that is moving from the plate to water ocean, usually into our neutral atmosphere and then out into the ionosphere. So it's a pretty amazing wave propagation system as it's moving through these different mediums, right? It will reach the ionosphere at that 92 thousand kilometer range. Um, and so the pressure wave, and maybe self-explanatory, right? This changes densities. And what we'll see is changes of densities along this line of sight. It'll be sudden. It'll happen roughly 10 minutes after an earthquake event. So that's the time of wave propagation from the start of the event to the ionosphere, typically, plus or minus 2 minutes. We usually see 8 to 12 minute um, time of arrival there. And we often see that this density displacement or change is moving at a velocity between 500 and 1500 meters per second through the ionosphere. This is all kind of a very broad summary of many, many papers about acoustic wave disturbances from seismic events observed in the ionosphere with GNSS. Um, and so, yeah, there's a lot of literature here that we're pulling from. Again, I just want to note um, observations of these density changes due to these acoustic waves are highly dependent on the line of sight. Um, like, yeah, AKA the geometry of the receiver and the satellite. And so again, going back, this is an integrated measurement, right? So this is a sum of all of the densities that are that the line of sight is moving through. What we can see sometimes is that at certain geometries, when we think an acoustic wave should exist, we see nothing. And that can be due to cancellation, right? If it's moving through a high density and then low density region, because it's an integrated measurement, we see a cancellation of this event. Just something to note as we move forward in the talk. So let's get into the project and kind of the impetus and how it was developed or put together. And we'll start with Guardian. So the Guardian system was developed at JPL, at NASA JPL, as a near real-time monitoring system of total electron content or TEC. You can see here the website. You can go here, you can get data from yesterday, data from today, across the world. You can see the different receivers here. This very colorful, I don't know, lines here. This is actually line of sight tracking over time between satellites and the ground-based receivers. So you can see, right, the west coast of the US has got a lot of coverage. And so Guardian provides TEC, and it provides it as filtered TEC. So we often filter out those daily changes that we see between night and day, right? So that's a constant kind of high density, low density, high density during day, lower densities at night. That's a constant trend. And so we remove that trend because ultimately, for Guardian's purpose, right, this is about a monitoring system of events. We don't need to monitor sunset, sunrise. That's not what we're trying to do. So they remove that. It's filtered. It's a detrended TEC. So we're going to call that DTEC. And I think one recent event was the Kamchatka earthquake that occurred, massive 8.8 magnitude earthquake in Russia. And the Guardian system actually detected a anomaly, the earthquake itself. And then afterwards, using Guardian data, JPL was able to monitor a tsunami wave as it moved across the ocean. And so, right, this is all to do with monitoring systems in natural hazard events specifically. And even though we have these, right, the deep ocean pressure sensors, which alert to tsunamis, this is seen as another tool that we have functioning today that can also be used to aid those DART sensors in terms of tsunami movement, especially over ocean. And so this is the project that we're going to look at today is very much this. It is tied to this effort. It's in the same vein. We've worked previously with JPL, working with them in the future soon as well. And so we're always kind of developing and devising new ways that we can create a functional near real-time natural hazard monitoring system. And so that's really how this project, is situated. And so getting into kind of the experiment itself, we're going to go into the South Pacific. And so you can see Australia here, and a lot of the South Pacific islands through here. And the Pacific Plate and Australia Plate interface here at the different trenches that are called out. And for this project, I'm going to look at the 2023 May and June. There were 4 earthquakes in this region, called out here in the red star, May 10th, May 19th and 20th, very close to each other, and June 15th, all above 7 magnitude. So fairly large. And maybe it's worth just mentioning here that I think the most recent research right now is showing that, magnitude 7.5 is maybe the lowest that an acoustic generated wave would cause a disturbance in the ionosphere. That's probably the lowest one that's been currently detected at this time in the ionosphere. And then just a brief overview of these four earthquakes. What's important to note is that the May 10th and the June 15th are considered at intermediate depth. So this is actually a fault within the subducted Pacific lithosphere. So a much different mechanism and location than the 19th and 20th, which were, you can see the depths, under 30 kilometers, and considered normal faulting at the interface of the Australian Pacific plates. So it kind of gives context to we may be trying to detect almost like two different animals here in terms of earthquake behavior and acoustic wave generation. And so finally, we're gonna use these ground receiver stations shown in the black triangle. Again, just point out here's Australia. We're gonna zoom in actually on these five. So we're fairly scattered. New Caledonia, got Fiji, Tonga. These are our five stations that we're going to use for this experiment, and we're going to see if we can detect these four earthquake events. So 1, 2, 3, 4. All right, so detection. We're going to run through method and then the results of the detection. Right, so this is about we have a measurement. How do we alert? Hey, this measurement looks weird. Looks like a coseismic acoustic wave disturbance. And the essentially the goal was to keep it pretty simple. We want to be monitoring something in near real time, and we want to raise a flag when we say this looks weird. And that's essentially it. We're not trying to identify what it is. We're not trying to identify much else, right? The frequency, the velocity, nothing like that. It's very simple. Just is this an anomaly or not? And we're going to do this in a very, I think, intuitive way. What we do is we in two parts. First part being we use a time series prediction. So we build a prediction model on historic ionospheric tech measurements, right? And we're going to predict future measurements. Okay, time series prediction is been going on for decades now. It's very advanced area. We can probably predict tech fairly well. So then the second follow-up part is really the anomaly part. If our prediction model, which we assume understands um, all ionospheric behavior, right? It's a big assumption, but that's what we're saying. We're saying this model knows typical ionospheric behavior. So when the model is wrong, we must be seeing something atypical, right? And how do we know the model is wrong? Well, we'll compare it to the ground truth. So we have the prediction, um, right? The difference between the ground truth and the prediction, aka error, that's going to be how we judge whether or not something is an anomaly. And how we judge that is using an algorithm that was developed in 2017 called the streaming peak over threshold with drift, or D-spot. Um, it's a somewhat statistically based algorithm that essentially looks at the distribution of errors in the past, maybe the past 5 minutes, um, and it determines what the threshold is for this time. And with drift, essentially means that this distribution is calculated over time. So if we start seeing larger and larger errors, theoretically, the error threshold will move with that. So it's not static in any way. We're not saying, hey, if you see an error over, one tech unit, that's an anomaly. No, what we're saying is this is relative to what we're measuring in this window. And so we want something that's going to be moving, right, with the change in distribution of errors. Um, and so what we're essentially saying is you can see here the receivers and our different satellite names. These are different tech measurements. And what we're saying is let's scan each one for an anomaly. There's a huge advantage with this method because it is fairly simple and broad. Um, we're not labeling any of our training data. We're just feeding in tech measurements. We don't need a library. We don't have to pull lots of historic, um, earthquake signatures, events. We don't need to pull them and label them so that we can train on them. We're literally just using the raw tech measurements as the foundation for anomaly detection. It saves a lot of time and energy when you're developing an algorithm to not have labels or a library that you have to put together. The big question really comes down to how do you determine what is normal, especially for this region? And so we are looking here at kind of a coverage map, so this spatial area that we're covering, and also time. And so this is about 4 days of coverage uh, between these select stations and these select satellites. We have 5 stations. We have roughly 110 satellites. I don't want to build a model. I don't want to build like 550 models to measure each single, receiver satellite signal for an anomaly. I want something that can kind of be a lot more broad and functional and I can just feed into. So in order to try and capture uh, regional behavior, we decided to take, at least we represent every station, but we're going to pick 9 different satellites. And since this coverage, it does cover 24 hours in a day. The coverage is fairly decent, probably best around these stations. We've decided that this is now the representation um, of the typical ionospheric regional behavior. And so this data is what we're going to use to train our prediction model on. Model design. There are a lot of different approaches that one can take to model design. Um, for this approach, we kind of will work up to kind of how it serves us best. But it really just comes down to what do you want to input and what do you want to what is your output? So for prediction, right, we're inputting a vector, a time series vector, y1 through yn, and we're predicting yn plus 1. You can see here. What we've chosen is to actually train 9 different models on those selected station satellite signal pairs. And we're going to feed in the vector into each model, and we're going to get out a prediction. And so what this actually gives us are 9 different predictions, which then translate to 9 different errors, right? We have 9 models. We're inputting the same time series. So it's the same series going in 9 different predictions, 9 errors. And that means that we can actually implement majority voting. This is a common tool that's often used in AI fields and ML especially, right? And so we have a vector here represented of these 9 different error values. We use our dspot error thresholding method that we talked about earlier, and we're going to return, 0 or 1. Is it not an anomaly, 0, or is it an anomaly, 1? And we have 9 different votes, right? So 5 out of 9, majority vote, it is an anomaly. We can see here. Um, we're not only thinking in terms of this one view, but also over time, right? So if this is a streaming data source, we're kind of looking at streaming data, a window moving through time. So not only are we going to implement a majority vote across our 9 models, we can implement a majority vote in time as well, right? So what we also want to see across here's 5 different time steps. Um, 3 out of the 5, right? If that 3 out of the 5 show majority anomaly decision identification, then it is an anomaly. And so how this then translates in a streaming view, you can kind of see here as we're taking 5 chunks, right? These 5 chunks, these are 9 models over time. We can see that as we move along time, right? Here's our first anomaly detected, but in looking back the last 5, it's 1 out of 5. So we don't have a anomaly detected here. It's not until this time step here that we finally have 3 out of the 5 last uh, time steps do we have an anomaly, a majority anomaly across the 9 models. So it's a little bit involved, honestly, but it does help when it comes to uh, kind of getting true anomaly results, if that makes sense. And this is kind of it all tied together. It can be a little bit more confusing diagram, so it's nice to just walk it through, but it's saying the same thing. Same data, right? This is an example of a receiver satellite signal. It's going into these 9 models. 9 models have not their vote of anomaly or not over time, right? And we can see how that plays out in terms of uh, how eventually something is labeled as an anomaly. So hopefully now, once we've understood that, we're just going to move into our results. These are the 9 different earthquake events that we were reviewing, the May 10th, 19th, 20th, and June 15th. And what we see in May 10th is the earthquake event. Here are some sample receiver satellite tech value measurements. We see no anomaly. No anomaly detected after the earthquake. We see anomalies before, probably something else, but nothing, no coseismic acoustic wave disturbance. On the 19th, we see something much, different. We see the earthquake event, and we see a very clear, sudden change in electron density, right? This is a sudden increase and then return to normal. So we see 3 detections here, 1, 2, 3. We see something with our eyes here, but it was not picked up by the algorithm. And I should just note, we see some other things here that actually don't look like ionospheric behavior, but are most likely hardware issues. Often cycle slips kind of look like this. And so that's getting picked up as an anomaly. Maybe rightfully so. It's unusual and it, uh, is not normal. We see another very clear acoustic disturbance here after the 20th. And unfortunately, on June 15th, the Tonga station, which is closest to this earthquake event, was down for all of June. So we see nothing, unfortunately, on that event either. And this is where we're seeing the detections in plan. So here we have New Caledonia, Fiji, and what you're seeing in this kind of gray cloud, these are actually the tech measurements. So you can see, the lighter color is these very low tech measurements, but you can kind of get a sense of coverage here. And you can see here's the station, LAUT, the epicenter, and where we were seeing a detection there, the station NRMG, the epicenter and where we're seeing a detection. So it's between the epicenter and the station itself. Again, this really is impacted by line of sight between the station and whatever satellite we're looking at. And just a quick understanding, the velocities are well within that large range of 500 to 1500 meters per second, the first being 855, the second a little over 1,000 meters per second velocities. And lastly, we wanted the impetus, right, is about tsunami tracking detection. In the end, right, we detect the earthquake of May 19th, but we see that there is a tsunami arrived at the DART station in ZJ about an hour and a half later. And what we see in our measurements here, actually, these wave signatures here, this looks to us, and it's similar to many other wave signatures that have been confirmed, due to tsunami events. So tsunamis have their own pressure wave generation. It's called internal gravity wave, or IGW. And this also perturbs the ionosphere at the same wavelength as the tsunami, or similar to. So really interesting. Visually, we can see here the detection algorithm did not flag this at all as anomalous behavior. And so there's a lesson learned here, right? We might be able to kind of detect the source of a tsunami, the earthquake, event, but tracking it will prove to likely need a different tool and algorithm moving forward. Just a side note, this was a broad tool. It detected a lot of anomalies, including this nighttime anomaly, which was reoccurring, not every night. This is a quiet example. But you can see here, very similar times. This is a reoccurring anomalous event versus suspected to be an equatorial plasma bubble that is, yeah, I would say common in this region, in this equatorial region. And then here's just some more data behind it being a potential equatorial plasma bubble. This is measurements of rate of change of TEC, or ROTI index. You can see when you pass this kind of threshold here, it can get labeled as a bubble. It is now defined as a bubble. And what we see is a decrease in density, sudden decreases in density, very common of the EPB event. All right, so now that we have detected an anomaly, what can we do with this information? One thing we can do is try to locate the source of this anomaly. And so we're going to use the May 19th event as our test run for this algorithm. We have clear detections at these three, the same receiver, three different satellites. And what we do know is the time of these events, and we know the location of these measurements. And I didn't mention it earlier, but Guardian also provides what's known as ionospheric pierce point for all their measurements. And you can just see here a quick calculation, but this assumes this provides a lat long for these measurements, assumed at a 350 kilometer, what's called ionospheric shell height. And so we can have a location and time. So pretty valuable information when we want to geolocate something. And what we're going to depend on is a very common tool. So we're going to use something well known, the uniform linear array. But I think, right, we only have three signals and they're not in an array. So what we're going to do is build one. So we're going to take two signals and we're going to say these are the endpoints of our array. right? We're going to transform the signals just so we get rid of all of this other stuff. We just care kind of about when we're seeing this peak. And this almost transforms this measurement into an impulse signal, very similar to one, right? And so we have our two transform signals. They are the endpoints of our array. You can see here a really handy diagram from Chen 2010. You can imagine this is one endpoint, this is another endpoint. That's essentially what we're seeing here. How do we get the middle measurements? We're going to interpolate. This is an impulse signal. We're just going to interpolate the, just, and so now we have five different kind of, or five sensors, three of which are simulated to create a five sensor uniform linear array between these two signals. And we're going to repeat. So we have three detections, which means we can build three different uniform linear arrays. And to help visualize this, we're going to look at it in plan. So here we have the reported epicenter. Here we have these line of sight measurements between the LAUT station and the different satellites. We have three detections. This was a fourth, but it was not flagged by the anomaly, but it's plotted here. So we have three detections here. And what we're saying is we take two detections and we build a uniform linear array, right? We have our array, we have our observed signal, and we have the location. So we have a lot of really important information to now perform the maximum likelihood direction of arrival. So the primary issue of finding out where the origin of your disturbance is coming from is determining what is the angle of arrival to this array. And so what we're going to do is just search for it. So we're using a greedy search algorithm here. But yeah, it's essentially going to try and match the observed or our X observed signals to a simulated signal given the angle of arrival. So it's going to run through -90 to 90 degrees and test. It's going to simulate that signal, what five sensors would look like if it came from, 25 degrees, -30 degrees, etc. It's just going to go through each one. And when you find the highest correlation between what you've observed and the simulation, you have your angle of arrival. And yeah, it's just a greedy search. It's pretty simple. The one issue we have is we need to know the velocity of this wave that we're observing. And we don't. We don't know that in real time. So we're going to use five different options here between 500 and 1500 meters per second. And we're going to see what it looks like at these five different options. And here are the results. So we have three uniform linear arrays. We have three different results. We have five results per array, and this corresponds to the assumed velocity of the wave, right? And this is just an example of what a simulated signal looks like in the search for this array. Now, one more assumption we have to make is how long did it take for the wave to travel from its source to our array? And we're going to assume 10 minutes, which is the average time that we often observe between the time of an earthquake and its arrival in the ionosphere. And so we put all of this information together. We have the location of our array. We have the angle of arrival. We have 10 minutes to travel, so we know the distance we're going. So we have angle of arrival to distance. We can start plotting our estimation location. If you take all the three arrays, you do this for these five different velocities, you can generate this plot. And here what we see are the three different likely paths of source location. We see two intersections. Ideally, we would have one magical intersection, but we don't. We have two intersections here and here. So we take the average And now what we see in yellow is our estimated source location of this acoustic wave due to earthquake. The red is the actual location. And so we are within, we are under 1 degree difference from the true location or the reported epicenter of this earthquake. But what I just did for fun was superimpose now that original image that we were looking at earlier of the trench lines. And we see that, our estimated is still on this or close by, I think, to this line. It's still within reason. Um, uh, a reasonable estimation, knowing where this line exists. But I think also two things, right? We assumed 10 minutes. If we assumed 12 minutes, we might get a little bit closer. Assumed 8, we'd probably get further away, but there's a range here in terms of where exactly yellow could be placed, that we could further calculate. Um, and then secondly, with these earthquakes, we see typical lengths. I think USGS was reporting around like 50-kilometer lengths. And so it would not be unreasonable that this, epicenter is actually more um, shaped in this way. And so, there's some wiggle room here, I would say, in terms of these results. But overall, right, we have coseismic, ionospheric, acoustic disturbances identified as an anomaly, but not the following tsunami. And so we would likely want to develop a tailored solution for tsunami detection and tracking. Um, if 3 disturbances are detected, we can estimate a geolocation of the source of these disturbances. Um, right, detection is working for a variety of behaviors. So it's very flexible in terms of identifying anomalies, but it's not specialized. Um, and just to recognize there are so many variables that impact how successful detection is going to be of these acoustic wave disturbances, including line of sight geometry and how a specific earthquake generates an acoustic wave and how that propagates through the different mediums into the ionosphere. And here are some references during the presentation. And I'll just wrap it up here and say thanks for your time and attention. And yeah, hopefully this was interesting and uh, something new to learn for this lunchtime.
Right. Thank you so much, Fiona. That is fascinating, really thinking about all the impacts like earthquakes and tsunamis that can travel above and impact the ionosphere. Super,
Yeah.
super cool. So now we have open time for question and answer. So if you have any questions for Fiona, please ask them in the Q&A. I have one question to start off with that I'm just kind of curious, since I don't do a lot of this kind of computer or modeling based work. What level of computing power or data access is needed to run these models?
Yeah. So a dedicated GPU is really all you need. I run a lot of models on my laptop. Obviously, at Oregon State, I have access to high processing power if needed. But ideally, we don't want to spend a lot of compute or compute power or hardware needs on something that we're hoping to kind of implement um, uh, as something simple, if that makes sense. So training the model is the heaviest lift, but once you've trained a model, running predictions is very easy. Um, so yeah, I don't have exact figures for compute needs, but it's very reasonable.
So you don't need massive supercomputers to be able to do this.
No, no. And I would say you can use fairly simple deep learning models to do ionospheric tech prediction, surprisingly, is what I've been finding. You can make very difficult ones if you want to, but what I'm trying to do is get away with something simple and make it work.
Okay, so we have some questions coming in. So first, we have you mentioned a different algorithm would be required to apply this method for real-time tsunami detection and monitoring in an operational environment. Do you have any ideas regarding what this other approach might look like?
Yeah, that's a great question. Honestly, I have a lot of thoughts, which maybe is the problem. Uh, I think I think that once you have I think identifying a tsunami event without a co-seismic acoustic wave disturbance before it is very difficult. So that's one caveat. So the thinking is once you have identified an acoustic wave disturbance, you would flip into another algorithm, right? So you wouldn't want to try and build a new algorithm to just identify tsunami waves. It would kind of be this, twofer, right? So you have your anomaly detection of an acoustic disturbance, and then you switch on your tsunami tracking algorithm. Tsunamis have, uh, I would say, a fairly specific looking frequency, wavelengths, disturbance. Well, I probably don't need to show the slides, but I would say using that physical characteristic for a search algorithm would probably be best. Probably, I haven't tried it. What I'm thinking most about is like, have you ever used the bird app on your phone, right? And it can tell you which birds are singing based on the song that it hears, right? That's essentially what we would be doing. So we would be hearing that tsunami signature and we would say, oh, this actually sounds like a tsunami, right? Based on the wavelengths that we're seeing and hearing. So it'd be something like that, if that makes sense.
All right. So our next question, it comes with a kudos to a very interesting presentation. Thank you.
Thank you.
Um, and then have you tried to look at a tsunami without an earthquake source, such as something caused by a landslide or some other different mechanism?
Yeah, I have. So there's this amazing mechanism called a derecho, which is a massive pressure change in the neutral atmosphere, in our troposphere. And you can see these occur. They look like a giant wall of clouds. I mean, they're amazing, but they can cause tsunamis. They can cause inland tsunamis, like on the Great Lakes. I mean, it's fascinating. It's amazing. And so, yes, I think that would be that has I've tried it before. It was extremely challenging to adapt a similar algorithm as the one I've presented to detecting that signature. Those signatures come without, this precursor acoustic disturbance. They just kind of float in to the measurements. Um, and so, yes, I think that would be. Um, I have yet to wrap my head around how best to detect something like that and track it. Um, yeah, at this time.
Okay, and then one other question we have in is, what height do you put the ionosphere at for ray tracing location? And how would changing this height affect your results?
Yeah. So the height that we used for this is one that was determined by Guardian by JPL. That's the 350 km ionospheric shell height. Um, Studies, I think if you use other radar sensors, you can actually measure the height of the F layer fairly well throughout the day, and you'll see it's moving up and down all the time. So having a static 350 is not how to describe it. It's kind of the best average guesstimate, I would say. Um, if you move it down to 300, move it down to 250, which sometimes it would be, uh, location's going to change drastically. Where those line of sight, kind of where I was showing the tracking of the satellite receiver links kind of on that map, they would be moving around. Yeah. If they move around, then your estimation is going to move around. So it's very sensitive to how you determine what the ionosphere shell height is. Um, I think ideally you would have a measurement for that day that you are estimating, and you could make probably a better location estimation because of it. Yeah.
Okay, we still have some more time for questions. If anybody else has anything to ask, again, please put it in the Q&A. I have another question. Since I know that space weather events can, really impact GNSS precise positioning, can, these disturbances from earthquakes and tsunamis, impact positioning, or are they too transient and regional?
Oh, I thought you were going to go a different route with that question. They're too transient and regional. Yeah, I would say they're much smaller. So if we kind of in the presentation, I showed this nighttime anomaly event. The scale of that disturbance was huge compared to the acoustic disturbance from the earthquake. Um, where I thought you were going to go, the question was, can you detect anything during a space weather event? And I would say no, probably not, unfortunately. Yeah, so no, space weather events like geomagnetic storms, yeah, um they can really cause havoc. Uh and so yeah, we don't see that with Earth-based events. I am not aware of any Earth-based event that would cause signal loss like space weather does.